Welcome everyone to this talk on the simplest way to build resilient applications. It's Friday afternoon and resiliency is not the lightest topic of all, so I hope your energy levels are still quite okay. After this there will be a coffee break otherwise. If you have any questions you can drop them in the session Q&A and I will get to them at the end of the presentation. So what I will be talking about is a slightly newer way of handling the complexity of resiliency in the way we develop applications today. So I will start with a little bit of context of how we're doing things today, and then I'll show a different approach to this. So let's start with a simple example. Imagine I'm a reseller of Netflix subscriptions, Prime, Hulu, that kind of streaming services, and somewhere in my applications I have this function add subscriptions, and what it does is it first creates a recurring payment for this user so that he gets billed every month, and then for each of the subscriptions that he wants to have access to I loop over them and I create each of them. So now the question is, how can we make this piece of code reliable? It's just 5 lines. Does somebody see here some potential issues that we need to take care of? So if create subscription fails, we still created the payment. True, that's one of them. Any other ideas? Yes? So you mentioned that it can lead to duplicate payments or duplicate subscriptions in some cases. Also a valuable thing, so let's actually go a bit through it from top to bottom and talk a bit about what can happen here. So indeed the first thing is if this crashes somewhere halfway through, if there's, for example, an infrastructure failure, then we need to have a way of making sure that we don't lose this request. So either our upstream caller needs to have some kind of retry logic, or we need to put something like a queue in the middle to make sure that if this service crashes, that it can somewhere retrieve this request back and process it again. But if we do this, then we also need to take care of correctly handling these retries, because we don't want to bill our customer 2 times, and we don't want to create these subscriptions also all of them 2 times. So maybe we need to do some deduplication logic there. One thing we could do, for example, is have something like a request ID and then store this together with this payment ID that we generate in a key value store. Write some retry recovery logic around it so that if our service comes back up, that we first check the store whether there's an entry for this payment already. But I need to then probably also clean this key value store up every now and then to avoid that this grows out of bounds endlessly. And I need some retry and recovery logic, as I mentioned, all throughout these 5 lines in order to make sure that I don't do stuff multiple times and that I handle retries correctly. And these are just a few of the things that can actually go wrong. If you look a bit more across requests and at the bigger scheme of things, there are so many difficult issues in applications that we need to solve. So here are a few of them. Some of the harder ones are, for example, zombie processes and network partitions. But also just things like distributed transactions are actually very hard to get right. Who of you has encountered any of these in their careers as software developers in production or anywhere else? Like, yeah, everyone raises their hand, right? This is not made up, this is really the reality. So what we end up with is that often we have a lot of different solutions in our architectures that provide resiliency for different parts of the application. For example, application state could be stored in something like Redis or Amazon DynamoDB. Things like asynchronous events or asynchronous calls. We could use something like a queue, like we showed in the example. For example, Kafka or something like SQS. And some of these systems you see are also quite big on their own. Like Kafka, to fully know how it works and fully know how to manage it is not an easy thing. It's almost an entire knowledge base on its own. Also things like workflow orchestrators, if we want to make sure that if somewhere halfway along a process we want to keep retrying a step to make sure that we end up with all steps executed. Systems like Camunda or AWS steps functions. And then the last one I listed here are timers, to make sure that if I want to schedule like some background task to happen next week, that this actually also really happens. And so what you see in application logic is that you need to write a lot of glue and a lot of recovery logic across all these systems, which is pretty hard to get it fully right. And in those cases where you find another corner case in which stuff can go wrong, probably the best thing to do then is to apologize to your customer and send a voucher and fix it then on. So we get to this kind of state where our applications have a lot of different components and a lot of different things that work together in ways that are often a bit hard to keep an overview of. Who actually knows anymore where this request got stuck, how things fail together, like what exactly would the behavior be across all of these services? So one of the things you see in just the general industry is that a lot of new observability tooling is popping up in the last decade. You see many new startups, many new companies that are trying to actually help us make sense of the complexity of the applications that we're building today. And I think this is a bit a sign or a testament to the complexity that we are having. This is really an issue that needs solving. So, all right. I will not be describing a solution to all of these issues that I was talking about here, or not something that replaces all of them. You can still use all of these, but what I'm gonna show is something that at least significantly reduces the complexity of this. So if you look at a very high level way of how we develop applications, we have some clients, maybe talking over HTTP to some backend. This backend code then maybe talks to some other things like a database or an API. And what happens is if this backend, this service, if it goes down, then we lose everything that was actually in that service. We lose the partial progress of what it was doing at that point in time, and we lose all of the state that it was working on, which is why we need all these other components. So the thing I will be talking about today is called durable execution. And the framework that I'll be talking about is Restate. So durable execution is more like a space on its own. There are different projects in there. I will be explaining the way Restate works, but the others work often in comparable ways. So the way it works for Restate is you have a server sitting in front of your backend code, a bit in the same form factor as a workflow orchestrator or a message broker or like a reverse proxy, a bit like that. It proxies the calls that go to your backend, and it takes care of all the resiliency, the state, and the communication that your backend needs to do. And it pulls actually that complexity of doing that kind of state management and recovery in your own code. So this sounds a little bit like magic and a little bit fake, so I'll be showing a set of use cases which are pretty hard to get right, and I'll be showing a lot of code about how you implement them and how durable execution helps with them. So I'll be showing workflows and Sagas, concurrent async tasks, state machines with agents and actors as side use cases, and Kafka event processing. But before I start with workflows and Sagas, I first want to show a small animation of how durable execution actually works, because it's easier in an animation than in code. So the idea of durable execution is that you give code built-in retries and recovery of progress. So let's see what that means. So I said that the Restate server sits a bit like a message broker in front of your service, and here on the right is the same code that I showed in the beginning, so the adding of the subscriptions and the creating of that recurring payment. And now what happens when I get a request is it gets proxied via Restate, and Restate will first write down that this request took place. So it will persist it in the system as I need to call this add subscriptions method because user 897 wants to have a Netflix and a Disney subscription, similar to a message broker. And then what it does is it calls the add subscriptions method over HTTP, a bit like an RPC call. So this handler is exposed via HTTP to the server, and the server then sends this message, and what happens then is the code here starts executing. And every time you see here this green context, what actually happens is an event gets sent from my SDK, which is in this function, to the server. So for the payment, what that means is that I have the payment ID persisted as a new entry in my log. Then I have the recurring payment, which gives me back a payment reference. This becomes again a new entry in my log. Then the Netflix subscription. And now imagine that something goes wrong. So imagine that there is a crash. So what happens in this case is, for example, the service disappears due to an infrastructure failure. What will happen is Restate will see that this request took place, and it sees that it never actually ran to completion, that it never had the final response being sent back. So what it will do is it will trigger a retry, and now on a retry, what actually happens when every time I do ctx.run here is, instead of executing this function, I will be returning what I find in the journal. So every time we bump into ctx.run, the SDK, which is this context, will look, can I find something in the journal? If I find something, I return that. If I don't find anything, then that means I still need to execute it. So for the payment reference, it will there just return the previous payment ID. It will also see the payment already got created. It sees that Netflix already was subscribed to. And then it sees, okay, Disney, I don't find anything in the log, so I still need to create this subscription. It creates it and then responds to the original caller with a success response. So this is, in a bit, an animated way of the process that happens. So let's have a look at what this looks like in real life. So I have here the exact same code as a Spring application. So I have a subscription service with here my add handler and here those 3 steps. So let's run this. I'll be running it in debug mode because I have some breakpoints later on. So the application is now running. Now the next thing I need to do is start Restate. So I'm starting Restate here. Restate is a single binary, so I don't need to start anything else. It's only this process. And now I have a service and I have Restate, but I still need to tell Restate where my service is, otherwise it doesn't know how to talk to it. So I can do that via the UI. We can register a new service deployment. So this is a UI that comes together with the server. And if we register there our endpoint 9080, which is a service that I'm running, then we see here a set of services that get added. So these are the ones that I'll be showing. Here is our subscription service. You see this add handler, and with OpenAPI, we can also know what the request looks like. So we need to provide it a credit card, a list of subscriptions, and a user ID. So if I click OK, then now I have these services that I can talk to. So let's send a request to the subscription service. We can do that here via the playground. I will copy over the request because I am not so good at typing these days because I broke my wrist. Let's see. So we'll be creating a subscription to Prime, Hulu, and Netflix. And let's now send it. So if you send it, we'll see that we will get stuck, and that's because I put a little issue in the code. So let's have a look at what the issue is. We can go here to the invocations tab, and there we will find the call we just did. So I did a call 12 seconds ago to this subscription service. And if I look at what the issue is, then it will tell me that the Netflix subscription failed because the Netflix API is down. And so it's currently in its 8th attempt of trying to get that through. And here we see the journal, which is what I earlier showed on the left side of the animation. So that's the steps that it already did until now. So we see it created the payment. After that, it subscribed to Prime, then to Hulu, finally to Netflix. But at Netflix, something went wrong because the Netflix API is down. So let's solve this issue. In my case, the Netflix API is not really down, but what I did is in this create subscription method, I just put an if Netflix, then throw runtime exception. So if I comment this out and restart my application, then this will get retried with exponential backoff. So in a few seconds, we should see that it retries that final Netflix subscription and that things will end successfully. So here you see the invocation started again. It created the subscription to Netflix, not anymore to the other ones, and after that it succeeded. So here it's also gone now. So that's the real-life version of the animation that I showed. Now let's talk about some other things. The first thing that we'll be talking about is Sagas. Can any of you imagine what the relationship between durable execution and Sagas could be? No. So what are Sagas to begin with? Sagas are a pattern that makes it possible to roll back code to a consistent state on a failure. So it makes sure that if you fail somewhere halfway through a process, that instead of just stopping right there, that you undo all the steps you did until then. So the idea of Sagas is actually on an error, roll everything back to end in a consistent state. But when I show durable execution, what that actually is always trying to push code execution forward. So when it fails somewhere halfway, instead of rolling back, I will always try to continue execution and continue executing the next line. So the way that these two work together is as follows. So you can still use Sagas together with durable execution for cases where your business logic actually says, don't keep retrying this. If this happens, then just stop right there and roll everything back. And in that case, you can actually use durable execution to make sure that all rollback steps actually happen. So let's show an example of what a Saga implementation looks like with durable execution. So it's again the same example, so the same creation of the subscriptions, but now in the Saga version. So I can keep track of my rollback actions as a simple list of runnable steps. So every time I do something that I want to undo if my business logic demands it, I add a undo step to a list. This is deterministic on retries, because this list will always fill up with the same steps. So for creating the recurring payment, I add the undo step, remove it. For creating the subscription, I add the undo step, remove the subscription. And then finally, I run all these compensations in reversed order. And I run them only in the case of a terminal exception. And a terminal exception is a specific restate exception which says, don't retry this because it's we don't want to retry in this case. Just stop, roll everything back, and that's it. So let's send a request to this Saga service, the subscription Saga. So from now on, I will just use the curl command to send a request. So localhost 8080 is restate. The subscription Saga is the name of my service here, and add is the name of my handler that I'm calling. So if we execute this, then it will bump into this breakpoint, which gives us a bit of time to see what it actually did. So if we go back to the UI, then we see that 7 seconds ago it started executing this subscription Saga. And if I look at the journal, then I see that it created the payment, then Prime, then Hulu. Then at Disney it failed. It said Disney subscription is not available in this region. So that's an example of a case where I don't want to actually continue retrying making this subscription, because it's really my business logic which says don't bill a customer for a subscription he cannot have. So in that case, I remove each of these steps and end up in a consistent state again. And so with durable execution, each of these undo steps would get retried until they finally succeed. Let's let this make some progress. Okay, and so now our Saga has been executed fully. So the examples that I showed until now were all examples of more workflow-like things, so workflows and Sagas. The next thing I want to show is related more to concurrent async tasks and futures. So imagine an email verification use case where everyone has probably bumped into one of those. You sign up somewhere and then you get an email with a link and it asks you, click the link to verify your email. So this is an example implementation of that. So the way we implement that is by using here an awakeable, and an awakeable is in essence a durable version of a Java future. So if you think about futures in Java, then these live inside of your VM, and if your VM crashes or goes away for whatever reason, then this future also disappears. It's not a durable thing that exists across processes and across time. But with durable execution, what you can do is make this future align in that log that I showed earlier and have futures durable across retries and durable across time. You can bring them back on any other process where you would want them. So in this example of my email verification, I'm creating a durable future for my confirmation click. So this will get resolved when my customer clicks that link in his email. So I sent him here an email, and then I want to wait on 2 different timers. So I'm racing futures against each other. I have a verification timer which says give the customer at most 24 hours. If he then still didn't click, then just stop it. And send him a few reminders. So in a normal use case, you would have maybe 4 hours or something there, but to make it a bit more interesting, right now it's 10 seconds. And so what this example will show is durably racing futures against each other. If this crashes halfway through, these timers are still kept track of. So if I fail after 12 hours, this verification timer will time out after another 12 hours. So both the future and these timers are durable. So the example goes as follows. We wait for any of these to finish, either the confirmation, the reminder, or the verification. And based on which one finishes first, I take another path. I either have verified my email, I send a reminder, or I just stop the entire thing after 24 hours. Let's send a request to this email verification service. So again, I send it to Restate email verification, and then finally to my verify email handler. And if I execute this, this will of course block. So let's have a look at the logs. So if I scroll down on my logs, then we see here that it started the invocation and it then sent the email to me. And then after that, it starts printing, verify this by clicking this URL here. So this is a curl request that if I execute that one, then that future gets resolved. And so if I restart this service, you now see the reminders happening, then instead of doing all of that again, it will just recover those timers and those future and will continue sending these reminders. So let's actually stop this service entirely. If I now execute here this curl request, so I'll copy it over. So if I now execute this curl request, then we'll see that this process now will say that it finishes. But I stopped the service, so I first need to bring back the service, and then we'll see that this process, like my resolve action as well as the futures and everything, were durably stored. So it will just end the invocation there. Yeah, so now it says invocation has ended. So that's the example of concurrent async tasks. So you can do things like schedule stuff for later on, or implement long-running logic like this, wait for several things to happen, and have that all like pretty easily implemented with sequential code without like joining events together and the way things are often done now. So what else can we do with timers? So my third example will be a claim processor. So it's an insurance claims use case. So imagine I have a submit handler which handles different claims that get submitted. So what I want to do is I want to update a few different legacy systems. First, I want to create my claim in one legacy system, and then I want to poll that system to ask it, are you done yet? Because it will do a few pre-approval checks. So what I do here is I ask the system, is it still pending? If it's still pending, I will sleep. And once it's not pending anymore, then I will update the dashboard of my user. So that's the idea. And so this is an example of a process that can take arbitrarily long, because I don't know when the system will actually finally have made my claim. So what we'll do different here is we will invoke this via a Kafka event. So instead of invoking it over HTTP, we can hook this up to a Kafka topic and let this process events from Kafka. So who of you actually uses Kafka in their systems? Okay, quite a lot here, so that at least is a bit relevant. So when you are processing events from Kafka, there are a few different things you can use. The idea of having a consumer, a Kafka consumer, is one of the most common ones. So what a Kafka consumer usually looks like is you poll a Kafka topic, you get a list of events back, and then you loop over the list and process event after event. One of the things that's hard to do with this approach is having actually long-running tasks on each event. Because if I loop over my events and it takes a long time to process an event, then I will basically be building up a lot of backlog and I won't be processing my events in parallel. So I'll only be having parallelization across partitions, not within a partition. So with Restate, what happens is Restate subscribes to Kafka and parallelizes the calls of these different events for us, so that you can implement long-running workflows on Kafka without actually needing to manage this consumer loop of polling and acking the offsets and committing these. So let's start up my Kafka cluster. I think I actually still have it running. So let's see if I... So yes, it's still running. So now the only thing I need to do is then actually just tell Restate to read from it. So the way I do that is I tell it that on my claims topic, each event should be forwarded to the claim processor, submit. And so one thing that happens here is that whereas a consumer loop polls events, here we will process events in a push-based way. Restate will be pushing events to our function, so we don't need to do the polling. So if we register these topics, then if I now publish events there, we'll see how this will get processed in parallel, even though I only have one partition. So here I will be using a Kafka console producer to publish 2 messages to my claims topic. So I will be, one is fire damage to my kitchen, and the other one is for a different user, a car accident on the highway. So if we execute this and have a look at the logs of what's happening, then we'll see here that the different claims get processed in parallel. So here it says creating claim for user 1, and here it says creating claim for user 2, while the first one didn't finish yet. So this parallelized this workload across the different keys that ended up on the same partition. So besides this example of long-running workflows on Kafka, the last thing I want to show, which I think actually is one of the coolest things, is stateful entities. So keeping state consistent with execution is quite hard. You want to, for example, implement something like a state machine, and you want to make sure that no matter what kind of failures happen, that you never lose updates to your state or never have corrupted state. So with durable execution, a state update can be just another line in that log. It can be just another type of execution that you're doing, type of action. So you can very easily implement things like stateful actions and just put every change to the state as an entry in that log. So the example here is a package tracker. So imagine that you go to like a DHL office and you give them your package. The first thing they will do is register it, and then you have some dashboard where you see like updates of where your package is. So this is a small sample application of that. So for every package, I want to have a like an instance with where it is and what its final destination is. And so the example here is a what is called a virtual object, but that's basically just a stateful entity. And what happens is, of this package tracker, I will have a single instance per package that I create. So here, register package will set some state. This will be stored in Restate, and then update location will get updated over Kafka, and will also write some updates to state. And so the idea here is that this is a fully consistent state machine that can be like resilient across any type of failures without actually needing a Redis key value store and complex logic to keep everything in sync together. So when we send some requests, I'll first register a package called package123. So when I talk to a virtual object service, what I need to do is I need to provide it the key of which object I'm talking to. So imagine, you could almost see it as if this class package tracker, every Java object has become a durable object that lives forever, that gets stored in a server and that can be brought back when something goes wrong. And here package123 basically says which object I want to talk to. So I will register package123 as final destination Amsterdam. And now I will do again the same of update location, but this time over Kafka. So I'll send a few Kafka events of where this package was at 1 o'clock and at 2 o'clock. So once these have ended up on Kafka, what we should be able to see is if now I send a request to my final function here, which exposes this state to the outside, then it will tell me the joint version of the events that I sent. So this was the first event that I sent, this is the second, and then this is the third. So it's a bit like joining data across RPC, Kafka, and all sorts of other things. So those ideas of having key value state together with like these objects is very cool for implementing state machines, but also for more complex use cases, like for example actors, where you have a single actor per machine or something in a factory, and this actor does operations on this machine and stores some state about what it's doing. So these kind of use cases fit very well with this idea. And finally, you can also actually inspect the state of what it was doing in the UI. So here you can see for package123 the same info as what I was exposing via that handler. So it gives you a bit of introspection tooling into what your system is doing. That also works via SQL. So there's like a SQL shell which lets you via SQL just introspect everything that's happening in your system. Everything from this service called, the service called, the service called, the service, and then I got an error. All those kind of more complex types of things, you can like figure that out by just using SQL across all the data that is stored inside the server and inside the key value state itself. All right, that was it for the demos. So let's take one step back to where I started. So I started with this slide saying that it's hard to write resilient systems. I talked about all these kind of things that can happen. Let's have a look at how durable execution fits in those. So a lot of these things actually become a lot easier with durable execution. For example, have executed orchestration and distributed transactions fit perfectly well with logging each step and avoiding that things happen multiple times or that things don't happen at all. Things like timeouts get solved by retrying automatically. Duplicate requests is something that I didn't show, but in the case of Restate, you can add an idempotency key to the header of your request, and Restate then automatically deduplicates them. So where I said in the entire beginning, when we were talking about everything that can go wrong, I said you need to deduplicate retries and find a way to like make sure that you know you already processed this. So if you add an idempotency key, you don't need to write any logic for that. This gets deduplicated automatically. Then zombie processes and network partitions, which are things that are quite hard to get right. This is a bit more complex, but this gets solved because if the SDK, like the service, cannot talk to Restate anymore, then it will stop what it's doing. So you cannot get in the state where two services that don't know about each other are doing the same task. Restate will stop them, and Restate itself is a distributed system with a consensus algorithm that makes sure that if there's no majority, it will not allow progress. I showed a corrupted state with the package tracker about how state updates just become another form of execution and are consistent with where you are. And then things like race conditions, concurrency, and scalability also become a lot easier. So what is inside the box? It's a single binary written in Rust, so there's no need for a database or a queue, which is quite a big difference compared to many workflow orchestrators and other competitors of Restate in the space of durable execution and workflow orchestration. It's a distributed system that snapshots to S3. And it's open source, so if you go to docs.restate.dev, you can find a quick start and try it out yourself, and also self-host it wherever you want, because you can basically run it in a Docker container or however you want to run your things now. So a bit more detailed what is inside it. So I showed that actually it's like this box where you have data coming in from two sides. You have requests from clients and updates from services. Inside, it's a bit like a stream processing engine. So there's a big event loop which gets events either from clients or from services. And for every event that it gets, it will look at what that event actually is. If it's, for example, changing state, it will write this to RocksDB. If it's setting a timer, then it will persist the timer. If it's calling another service, it will take care of calling the other service, and so on. So it's a bit like a stream processing engine for durable execution updates. This approach that we took here, we try to keep it low latency to basically make it possible to use workflow guarantees for any function in an application. So from a slightly higher level, if you look at distributed architecture, so you have different instances of this Restate server running, and they store snapshots to S3, and to keep low latency for the live events, they replicate to each other via a consensus algorithm. And so your application itself is not running on workers or something, it's just running, for example, on pods on Kubernetes, or something like AWS Lambda or serverless infrastructure is also a possibility. So we currently support 6 languages. We have 6 SDKs: TypeScript, Java, Kotlin, Python, Go, and Rust. And this allows people to implement quite a lot of different use cases, so it's a very generic purpose thing. I showed quite some of these. I showed Sagas and orchestration, distributed transactions, and event processing, but there are a few other ones which are interesting. Of course, payment processing, so anything which requires high correctness and where there's a lot of stakes are good use cases for durable execution. Also things like control planes, so use cases where you have a lot of retries, a lot of timeouts, like you bring up a machine and wait till it's up and keep polling it. Once it's up, you do something else. So these kind of lots of retries, lots of timeouts use cases work very well. And then the final one is workflow interpreters and agents. So the way Restate and durable execution is different from workflows is that traditionally in workflows you specify a static definition of your workflow and you push events through that graph. But so the resiliency does not come from the event itself. With durable execution, on the other hand, every event builds up its own recovery log, and recovery is just walking through that same log again. Every event can take a completely different fork throughout your code and has its recovery log that belongs to that path next to it. So that works very well for things like workflow interpreters, where you dynamically want to decide in which order you do things, for example, or an agent is deciding which path you want to pick of all the different options you have. So that is what people are currently building with Restate. There's like a lot of different types of things you can use it for. That was it for my talk for today. Here's a QR code which takes you to, I think, the website. So there you can find the docs and try it out yourself. And if you have any questions, then you can drop them in the Q&A, which I will be taking a look at now. So the first question is, what about performance, scalability, and persistence of tasks? So as I mentioned, it's a distributed system itself. So it has a consensus algorithm which will replicate each event that it gets to some of its followers. So that's where the persistence comes from. When it comes to performance and scalability, we have done some tryouts for latency and throughput. So the idea that what we want to get to with Restate is having a low latency workflow orchestrator which can handle pretty good throughput. Restate was also developed by the same creators as Apache Flink, so they got a lot of their the ideas of how to implement it there. So right now what we're able to get is around 15 milliseconds median execution time for a three-step workflow, up to 31 for a 9-step, and also the P99 stays below 100 milliseconds, which is pretty good, especially if you compare it to workflow orchestrators, which often work in the way that if they get a request to submit a workflow, then they will start up this workflow, maybe start up a container. Like, it can often take up to a second. There are not a lot of guarantees, where this works really in a very event-driven based way to keep latency as low as possible, so that it can be used almost anywhere throughout code, and not only for like the very key orchestration things. So the metrics here for throughput were for a 3-node cluster which had 3-way replication. So that means that every event had to be replicated to the entire cluster, so we didn't actually gain much from having 3 entities or services running. And then we got up to something like 17K throughput, which is enough for most use cases. I do need to say that this is already 8 months old or something, and Restate has been around now for 1 year and a half, so these results are pretty old, and I probably have improved by now. So that's about performance, scalability, and persistence. If my app is on Kubernetes and has n pods running, how many pods of Restate do you recommend to have? In case of multiple different services, do you recommend having a shared Restate server for all pods, or just one for each of them? So right now, the way we saw it was having one Restate cluster per application, where services need to talk to each other. So one of the things you can do, which I didn't show, is have reliable RPC across services. So in that case, you would have one Restate cluster. Maybe you can start with 3 servers and scale up if you need that for throughput, and have like one cluster per application domain, let's say, which can have like maybe 5 services, 10 services, depending on your use case. Yeah, the number of pods, like minimum 3, and you can scale up as you go. Can we configure the Restate server to decide which cases to retry and which cases just do rollback? The whole process must take a maximum of 5 seconds or 3 attempts. Yeah, so to every action that you do, you can, well, every asynchronous action, you can add a timeout. For example, if I call another service, I can add a timeout that says if this didn't succeed within 5 seconds, then stop. And with those terminal exceptions that I showed earlier, you can then write that kind of logic which says, if I hit a timeout, then throw this non-retriable exception and don't retry it anymore. And you can also like specify for some operations that you don't want to do retries, which is, for example, that ctx.run command which I showed. You can like specify a retry policy which says only try it 10 times. If after 10 times it didn't succeed, then throw a terminal exception and roll stuff back. This kind of logic. All right, I think that were all the questions. No, if the restate server goes down, how can you ensure executions of lambdas aren't lost to restate? So every service has an SDK embedded as a dependency. And the SDK, if it cannot talk to restate anymore, will finish the execution, will throw an exception basically and let the service stop executing at that point. So that's the way we make sure that if something goes wrong, that the service doesn't continue executing. How do you make sure that executions aren't lost to restate? So I think the question there probably also relates a bit to, if I do ctx.run, what happens if I fail in between creating the payment and sending the answer back to restate? So in that case, most of the examples that I showed here had the format where I first generate an idempotency key, which durably gets stored, and then I use that key to, in my request, to let my payment provider, in this case, do the deduplication. So most APIs of this kind of things, like Stripe and stuff, they allow adding things like an idempotency key and do deduplication in that case. And so what you gain here is that it's very easy to actually generate these idempotency keys and have them stable on retries. So this is one pattern. Another pattern is the pattern of where you first create a reservation and then confirm it. So things like booking a car, those kind of APIs often work like that, that you first create a booking and then say, okay, confirm this one. So there it also happens in 2 steps. So that means if something went wrong between the first and the second, then this booking will just expire and will not have happened. So that are the 2 options of how you can solve this issue of failing in between doing the payment and storing it in restate. Wow, this is not chronological. That's a bit hard. Is it mandatory S3 or can we use cloud storage from GCP? It's not mandatory S3. You can also just use persistent disks or yeah. So I think that are the main 2 options right now. But so no, you can just use cloud storage from GCP, I think. Is reactive programming style supported, reactor, and what about virtual threads? So you can use virtual threads. We don't have any strict requirements there. So yeah, you can do what you want to do. I must say, I'm reactor, I'm not entirely sure about this. I would need to ask my colleague who implemented Java SDK if he has tried this out. All right, I think that were all the questions. If you have any other questions, I will be outside and you can always drop by and say hi.